Hello everyone, welcome to demo 2 of deep learning. In this demo, we'll be exploring the backpropagation algorithm. So as you may recall from class, the backpropagation algorithm is the workhorse of deep learning and used to train all kinds of neural networks, both small and large. In this demo today, we'll be implementing backpropagation by hand in NumPy. Just a statutory warning. This is not for the faint-hearted. In fact, there's a reason why packages such as TensorFlow and PyTorch are so popular. It's the fact that they have extremely well designed implementations of the backpropagation algorithm. So I would advise that for any real-world application, don't do what we're doing today. Okay, so don't try to code up the algorithm by hand. Instead, use these well-established packages. But this is just a taste of what's going on under the hood in these implementations. Okay, so let's get started. So as usual, we'll open up our Colab notebook, and I have a few helper functions already in place. So let's just run those. So the first loads a standard data set. It's the Mnist data set, which most of us must be familiar with. It's a data set of handwritten digit images. And the goal is to classify the digit in these images. So for example, the input is basically this kind of image. It's a fairly small image, 28 by 28 size. And the output is 1 of 10 classes. Okay, so this is what we'll do. We'll build a small neural network that will do this kind of classification, and we'll train it by hand in Python using backpropagation. It's also helpful to define a few utility functions. So we will use sigmoid activations in our neural network. So I have defined the sigmoid, its derivative, and also its generalization, which is a softmax. The softmax is a common activation function used as the activation of choice for the last layer in a classifier neural network. We'll train using the cross entropy laws, which I've defined here, and also some function that converts class labels to one-hot encoded vectors. Okay, so I'll get started with the network itself. So let's code up a simple neural network. Okay. So here you can define the network however you like. So what we'll do for this demo is a very simple 2-layer neural network. So it's going to be a network with just one hidden layer of neurons. Okay, so it's a 2-layer neural network, and the input, as you may recall, is an image of size 28 by 28. That's 784 length. Okay, so let's assume that the output is a hidden layer of 100 neurons. Right. So the weights of the first layer is a matrix of size 784 by 100. It's common to initialize the weights according to a Gaussian distribution, where the variance of the Gaussian is the larger of the two sizes. Right. So let's initialize. So, and it has a name. It's called the Glorio initialization. the Xavier initialization, which we'll discuss in class. We'll also do the same for the second layer of weights. So the second layer will take the outputs of the first layer, which are 100 of them, and then convert to class labels, class probabilities, which is 10 of them. Right. Again, we'll initialize this according to we'll initialize the variance of this distribution according to the larger of the matrix sizes. Okay, so this is the initializer, and we'll also initialize biases. So the biases are typically just initialized as 0. So 100 neurons in the first layer, 10 neurons in the second layer, and that's about it. Cool. So actually that's all we need, right? So we've set up the network. And here you can set up more complicated networks as you like, depending on the application. But for illustration, we'll just look at this very, very simple application. Okay, so recall that this kind of network or any network induces a computation graph. So if I imagine X to be the input and Y hat to be my prediction, then the transformation X to Y can be broken down into a series of layers, and each layer has a linear activation, a linear transformation, and a nonlinear activation, right? So the linear transforms to nonlinear, another linear, and so on, right? So so U1 is just the weights times X. Z1 is the nonlinearity, which is the sigmoid times sigmoid of U1. Similarly, the weight times Z1 is U2. Y hat is softmax of U2, and you use Y hat to compute the loss function L using the cross entropy loss, right? So this is the computation graph. What we'll need in backpropagation is the derivatives of each step in this computation graph. Okay, so I need to compute the derivative of the loss with respect to Y hat, U2, Z1, U1, and so on, as well as the derivative with respect to the weights and biases. So I've written down several equations here which compute these derivatives. Now, as you can see, it already becomes fairly tedious, right? So it's not hard. I mean, there's an algorithm to actually come up with these these derivatives, but one needs to be careful here, right? So to make sure that the derivatives you compute here are well formulated. So I'm just going to write down these equations here, and we'll now implement these in NumPy. Okay, so that's what we'll do. So let's define a function which will compute the gradient of the loss with gradient of the loss with respect to the weights and biases. The loss is defined over exactly one sample. Okay, so exactly one sample and it's labeled, right? So this is basically all we'll need to implement. If we can implement this correctly, then we are basically done, because this will help us take gradients, right? So we can accumulate gradients over multiple samples. We can update weights according to these gradients, and so on, right? So this is the function we'll implement. Okay. So recall that there are basically two steps in backpropagation, right? So there is so there is a forward pass and a backward pass. So the forward pass merely takes in the sample and then propagates it through the network. Okay, so recall that the network consumes the input is basically 28 times 28, but 784 dimensions. So let me just flatten the input. Okay, and then do the forward pass of this input through the network. So how do I compute the forward pass? Well, I already defined the network here in terms of the weights and biases. So let me just multiply it out by hand. Here, since it's a small network, I won't do any for loops, just write out the equations. But for larger networks, you'll have to be a bit more judicious here as to how you define these transformations. But the forward pass is actually fairly straightforward, right? So I'll just implement matrix vector multiplication for the linear part, and then nonlinear activation of the sigmoid in this case for the nonlinear part, and the output of the nonlinear activations gets now passed through the second layer weights. Okay, so that's just C1 times in the second layer, the biases. Okay, and then and finally we get a softmax. Okay, so it's very simple. So this is a forward pass. Okay, so forward pass simply evaluates the network. Now recall that this network is randomly initialized here. So in the beginning, this is going to give you fairly garbage, right? Like it's not going to make any reasonable prediction. But as we train, we'll adjust the weight such that these predictions become more and more accurate. Okay, so that's a forward pass. So what do we do with the forward pass? So once we have a prediction, we now calculate the loss, right? So the loss we can calculate by looking at the so looking at the one-hot encoded label, right? So let's just do a one-hot encoding of the label. That's just the integer to one-hot function we defined earlier, the 10 classes, okay? And then the loss is just the cross entropy between the prediction, the encoded label and the prediction. Okay, so y log y hat, right? Something like this. So this is the loss. For bookkeeping purposes, it may be also helpful to just define a couple of other things. So let's just also maybe predict. It's not needed actually, but if you want to actually read out the prediction, it's just also useful to, if you want to compute accuracies and things like that, look at what the prediction actually does. So find the maximum probability, find the class corresponding to the maximum probability in y hat, and then that's a predicted class. We might also want to one-hot encode it if you want to do some kind of statistics. So these are not necessary, but let's just try it out. Okay. Cool. So we compute the loss, and now we're ready to implement the backward pass. So what the backward pass does is backpropagate the error, the loss, right? So backpropagate the error back through the network, and then use those to use the derivatives that we defined here in a composition of these derivatives that we defined here in terms of the chain rule, and that will produce the overall gradients of the loss with respect to W and B. Okay, so that's what we do, and here you have to be a bit careful, right? So you have to, for example, right? So here I was careful in defining these equations, right? The derivative of the loss with respect to U2 is y hat minus y, right? So you need to make sure that your variables are somewhat well indexed and so on, right? So so derivative of, so this notation du2 is actually dl, partial of L divided by partial of U2. Okay. That's du2. It's not good notation. I don't know if there's any good notation here because it's all very tedious. But anyway, this is the first equation. So I implement the first equation. Similarly, you can implement the second equation. So y hat minus y times z1 transpose. The convention I've used in this implementation is that everything is row vectors. So data is row vectors, and so matrices are tall and skinny, right? So I need to take basically the transpose of this equation. That's how the algebra works out. So it's actually z1. It's the opposite of this equation, really, right? So it's d1 transpose dot du2. Okay. And then the derivative of the loss with respect to B2 is simply just y hat minus y, which is just du2. So I'll just write that out. Okay, so we have now, so we have gradients with respect to the second layer weights and the second layer biases. Okay, so this we can calculate. So given these, we can now also calculate the gradients of the first layer weights and the first layer biases. Okay, so again, I have to backpropagate through U2 through Z1. Z1 will give us U1, and U1 will give us W and B. So we'll have to define each of those. So let's start with Z1. Z1 is basically the derivative of the loss with respect to Z1 is y hat minus y times W1. Again, it's the transpose of all this. So if you work through the indexing, this is just so W1, the weights of 1, transpose y hat minus y. Okay, so just this guy. And now so this is derivative of L with respect to Z1. Derivative of L with respect to U1 is the previous quantity times the derivative of the sigmoid. Okay, so multiply. Multiply the previous quantity dz1, the derivative of sigmoid of u. Okay, sigmoid of u1. So again, this is something subtle that we've done here. So U1, recall, where did this come from? This actually came from the forward pass. So it's important to store these intermediate quantities as we go through the network in the forward pass. Okay, so it's the derivative of the loss with respect to U1. We're almost there. So given U1, we can now compute the derivative of the loss with respect to W1. So that's just the previous quantity times X, right? So X is the input A here. So it's just a transpose dot V1. And the derivative of U1 with respect to the bias is just 1. It's the identity because U is Wx plus P, right? So this is just the previous quantity. And this is about it. Yeah. So this is actually all we need for the backward path. So it's not too bad. There's a bunch of indexing and some subtle, variable accumulation to be made here. But as you can see, this becomes quite tedious as the network becomes more complicated, right? So if you're going to 3 layers or 4 layers, even more, you have to be really careful as to how you take these, transposes and so on, which be careful with. Okay. So this is really what's going on when whenever you call z dot backward in PyTorch, really something like this is happening under the hood. Okay. So that's all you need. So the derivatives of the loss with respect to W2 B2, W1 B1, they're all here. Now these are the quantities we'll use to update our weights. So it may be just helpful to store some, if you want to do analysis, again, not necessary, but if you want to store analysis, let's just keep track of some intermediate variables. So let's say the weight gradients, right? You can store all of that in one giant array. The bias gradients, the same thing. Okay. Yeah, it's not too helpful, but it's fine. Yeah, let's just do that. So if I wanted to, just for simplicity, if I want to update my weights at one shot, I could just do it one by one. But since my weights variable is one variable, let me just make a big matrix here. So let me append my weight gradients with dw1 and the weight gradients, dw1 and dw2, and similarly I'll append my bias gradients with db1 and db2. And that's about it. So there you go. So we have our gradients with us, and now we can use these gradients however we want. We can use them to, let's say, update the weights, for example. So let's update our weights. So update weights. Again, this is not the best way to do things, but I'll just overwrite the weights. Okay, so I'll just replace the weights in place. So just 2 layers, so it's not too bad. So weights OI. Let me just update the negative direction of the gradients. That's it. I've chosen a learning rate here, right? So you can pick whatever learning rate you like. Better to start kind of small, otherwise things tend to oscillate quite a bit. Similarly, the biases update using the bias gradients. All right, there you go. Oh yeah, I computed the loss. Okay, let's just make sure the loss is going down. So we can ask this function to return whatever you like. Let's just return the loss for this demo. Okay, that's it. This is the backpropagation algorithm for 2-layer networks. Okay, that's about it. Let's make sure that this actually works. I don't think I have forgotten anything. Yeah, this looks fine. I think it's fine. Let's see how it does. So let's do some testing. Let's test it on the Mnist data set that we downloaded. Okay, so for testing, it's just going to just call this function a few times. See what happens. So I'll just define a function called train one epoch. So what's an epoch? An epoch is basically sweeping over the entire data set. So I'll train for all samples. Right. So that's one epoch. I can pick the same learning rate, or I can just maybe pick some other learning rate. It's fine, doesn't matter. So this, so epoch. So what all? So what this function does is just call the previous function several times, and as many times as the number of training examples, right? So let me just call this function over all the training examples. Okay, so xtrain of y. So what does it just takes the input sample and the label and the learning rate. Okay. So, sample, learning rate. Maybe I'll just also print out the loss just to make sure the loss is going down. Don't go down monotonically, right? Because we're not doing, we're doing sample by sample. So loss may fluctuate locally, right? But overall, the trend should be that it should go down. So we'll see if that happens. And let me print out, I will say every 500 samples. Let's see if this should give us a measure of how well we're doing. Ideally, what you should be doing is looking at many batches and accumulating losses. And actually, technically, what you should be doing is measuring test accuracy, which I'll let you do on your own. Right? But that's what we should be doing. Okay, so this should be good. Let's see how well this works. Okay, so let's test. Let's train, say, let's say one epoch. And if the network is doing the right thing, then the losses should generally go down. The losses are high. And you can see it kind of starts to go down. Generally starts going down. Let's try it a little bit more. Yeah, I can see fewer twos and more smaller values, right? 0.05 and point. These are instantaneous losses, not accumulated. Right? So these are losses over individual samples. So that could be the odd sample, which is an outlier. Right? But generally, you can see that the values are kind of going down, right? So the losses are more or less in the 0.0 somethings. Right? This is an indication that the model is doing something reasonable. Okay, so that's about it. So this is the backpropagation algorithm, and in about 20 lines. Again, statutory warning. Be careful if you want to implement this on your own, especially if you are constructing new networks. It's always just safer to use stable implementations of the backprop algorithm, such as the backward function in PyTorch. Thanks, everybody, and see you next time.